Ahoy, matey! This ship may be headed to port, but she's still got one more body of water to cross before she docks for good. Hope you're ready to set sail, landlubber. This may not be our maiden voyage, but it'll certainly be a swan song for the history books. Welcome to Class 6 of Unit 8, Graphs of Parabolas Redux. We're taking everything we've learned so far and putting it together as we close out our discussion of our 8th unit. So you've got a problem set to complete for me, which once again means this video is optional. You do not need to watch, nor do you need to take notes, but it's here for you as an additional resource if you'd like some extra practice. I'm going to keep going through these problems one by one without stopping, but you are strongly encouraged to pause the video, work each one out on your own, and then come back and check with me. Let's get started with some transformations, right? Based on what I see and where I see it, I want to say how the shape or position of my graph changes. Let's start with our first one here. Immediately, I see a negative in front of that 3/4, which tells me my graph is going to flip from concave up to concave down. I've got a reflection over the x-axis. This 3/4 here connected to the x squared is less than 1, so this is going to give me a vertical compression, which I'll abbreviate vcomp. By that factor of 3/4, I'm smushing closer to the x-axis. And last but not least, this +5 outside of the square, so it does exactly what I expect. Here's my vertical translation. This is going to shift my graph 5 units up. Y equals 6, quantity x plus 7 squared minus 8. Let's get started with that 6. It's connected by multiplication, so here's my stretch or compression. It's greater than 1, so it's going to give me a vertical stretch by 6. This +7 inside of the parentheses, again, it does the opposite of what I expect. So here's my horizontal translation. +7 I would expect to move me to the right, but it's actually going to move me 7 units to the left. And then this -8 outside of the parentheses, here's my vertical translation, up or down. This does what I expect. It's going to move me 8 units down. Cool. Moving on, though, we can also take this information and work backwards. Maybe I give you the transformations and you use that to reverse engineer the equations. So for my first one here, I've got a vertical compression by a factor of 2/5. So if I'm moving backwards, right, here's my value of a connected by multiplication. So there's my 2/5. And then I've got, in parentheses, my horizontal translation 4 to the right. Again, it does the opposite of what I expect. So if I want to go to the right, I actually need a -4 inside my parentheses. Last but not least, close out my square. My vertical translation sits right outside. If I want to go 8 units up, I should add 9. Reflection over the x-axis for the second one, again, always starts with y equals. That tells me that I've got a negative coefficient out in front. My vertical stretch by a factor of 7/2, right? So I'm multiplying everything here by 7/2. Inside of my parentheses is my horizontal translation. 1 unit to the left, I'm going to do the opposite of what I expect. I should actually add 1. Close out my square, and then last but not least, if I want to go 3 units down, I'll subtract 3. Cool. Let's do a little bit of graphing. So I've got examples in both intercept form / standard form and vertex form. I'll do these first 2 examples where everything I write is in set builder notation, and then the last 2 I'll do in interval notation. So first up here, y equals x squared minus 10x plus 21. It's in standard form, which means I probably want to factor it to get my x-intercepts. The way I find my x-intercepts is by making y equal to 0. So here 0 is going to be equal to x squared minus 10x plus 21. Notice this is a quadratic trinomial, so I'm going to set up my 2 parentheses. At the front, x squared has got to come from x times x. At the back, I need 2 numbers that multiply to 21 and add to -10. That's going to be -7 and -3. From here by the 0 property, if these 2 things multiply to get 0, one of them has to be 0. So either the x minus 7 is my 0 or the x minus 3 is my 0. If x minus 7 is 0, adding 7 to both sides, x is equal to 7. If x minus 3 is equal to 0, adding 3 to both sides, x is equal to 3. Which tells me that the points 7 for x and 0 for y, 3 for x and 0 for y are on my graph. So here's 3, 0, and then 1, 2, 3, 4 over. Here's 7, 0. Now, I know that my vertex, by symmetry, lives halfway in between my intercepts. Let me use those values to find it. So its x value is going to need to be right between 3 and 7. The number smack in the middle of those is 5. Let's confirm it algebraically by taking the average. I'm going to take the average of 7 and 3, add them together, and divide by 2. So this gives me 10 over 2, which reduces to 5. That is the number that I found logically. Now I'm going to find the y value, which I do by substituting back in. So y is going to be equal to 5 squared minus 10 times 5 plus 21. Well, 5 squared is equal to 25. Negative 10 times 5 is negative 50. Now combining all my like terms, 25 minus 50 is negative 25. Negative 25 plus 21 gives me a y value of negative 4. So this tells me that my point must be 5 for x, negative 4 for y, which lives right over here. Let me also take this opportunity to identify my axis of symmetry. X equals for a vertical line, it takes its value right from the vertex, and then I'll even take the opportunity here to sketch it in. I know that it will be useful for me at a later point as I'm building my graph. From here, let's find the y-intercept. I need to do it anyway. So to find the y-intercept, I make x equal to 0. So plugging in 0 for x is going to get me y equals 0 squared minus 10 times 0 plus 21. Notice 0 squared is 0 and negative 10 times 0 is 0. So y is going to be equal to 21. This tells me that the point 0, 21 is on my graph, but I don't have enough space to graph that here. So let me just find one more point on my graph instead. Though conventional wisdom is to take values close to the x value of the vertex to substitute in, that will usually give me nice numbers to work with. Let me try 4. It's right in between the 3 and the 5. It gives me some nice friendly numbers. So I'm going to take x equals 4 and use that to find a value of y. So it's going to be 4 squared minus 10 times 4 plus 21. 4 squared is 16. Negative 10 times 4 is negative 40, and then plus 21 at the back. 16 minus 40 is negative 24. Add negative 24 and 21 would get that y is equal to negative 3. This tells me x is 4, y is negative 3. This point here, 4, negative 3, is going to be on my graph. Last but not least, by symmetry, I went 1 to the left to find this point. There should be a companion point, 1 to the right, at 6, negative 3. Last move, I'll, to the best of my ability, draw in my parabola, pretend it's beautiful and perfect, and we've got our graph. All I need to do now is identify my remaining characteristics. Well, here my vertex is at the bottom, so it's a minimum. My graph is concave up, it's a happy face. My domain is always all real numbers. My range here is bounded by that negative 4 at the bottom, so my values of y cannot go below negative 4. The way that I would say that is that y must be greater than or equal to negative 4. I am increasing to the right of that axis of symmetry, x equals 5, so I'll write this as x is greater than that 5 if I'm to the right. I'm decreasing here to the left, which means that my values of x are less than 5. Beautiful. Onwards and upwards. Let's try another. Y equals 1/3 quantity x plus 1 squared minus 3. This guy is in vertex form, which means I can immediately identify my vertex. This plus 1 here tells me I went 1 to the left. This negative 3 tells me that I went 3 down. That tells me that the point negative 1, negative 3 is on my graph as my vertex. Negative 1, negative 3 would be right over here. I can now identify my axis of symmetry. Again, x equals for a vertical line. It takes its x value from the vertex. Let me sketch in that vertical line now. Again, I want to use symmetry at an eventual point to find some companion points. Okay, from here, let's find some intercepts. So I'm going to begin by finding the x-intercept by plugging in 0 for y. When I do so, I would get 0 is equal to 1/3 quantity x plus 1 squared minus 3. Now adding 3 to both sides, and I'm going to skip some steps here for the sake of efficiency. Let's add 3 to both sides. I'm not going to show all of my work, but I know what choices that I'm making here. So I'm adding 3 to both sides. Now to get rid of 1/3, I will actually show this. 1/3 multiplication is the same as division by 3. So let's multiply both sides by 3 to get rid of that 1/3. 3 times 3 is 9, and then I'm left with that x plus 1 squared on the right. To get rid of my square, I'll take the square root of both sides to reveal that plus or minus 3 is equal to x plus 1. And now I can do some splittage, right? So if x plus 1 is plus or minus 3, then x plus 1 could be positive 3 or negative 3. If x plus 1 is positive 3 minus 1 from both sides, x is 2. If x plus 1 is negative 3 minus 1 from both sides, x is negative 4, which tells me here that my x-intercepts appear at the points 2, 0 and negative 4, 0. So 2, 0 is right over here. Negative 4, 0 would be right over here. Now I'll find my y-intercepts, which I do by plugging in 0 for x. So y is going to be equal to 1/3 0 plus 1 quantity squared minus 3. Simplifying the right-hand side, I get 1/3 of 1 squared minus 3. 1/3 of 1 squared, well, 1 squared is 1, and then I've got 1/3 times that. So 1/3 minus 3 is how this simplifies. 1/3 minus 3. Common denominator here, I'll turn 3 into 9/3. This reveals that negative 8 over 3 is my value of y. This means that the point 0, negative 8/3 is on my graph. Now, negative 8/3 is really close to negative 3, so on my graph, I'll kind of situate it right about there. So here we'll say is 0, negative 8/3. And then by symmetry, if I went 1 to the right to find this point, there should be a companion point 1 to the left. So here the x value of that point would be at negative 2, and its y value should be the same at negative 8/3. Let's connect my parabola to the best of my ability. It doesn't need to be perfect, and it usually won't, because I'm no artist, I'm a mathematician. From there, all I gotta do is find my characteristics. Notice once again, my vertex is at the bottom of my graph. It is a concave up happy face parabola. My domain is always all real numbers. My range here, I'm going to identify as the values of y such that, right, I can't go below that y value of negative 3. So y needs to be greater than or equal to negative 3. I am increasing to the right of my axis of symmetry. So when values of x are greater than negative 1, my graph goes up. And I decrease when my values of x are less than negative 1 to the left of that axis of symmetry. Let's do 2 more. Y is equal to negative 3x squared plus 12. I'll write everything here in interval notation. So I can choose to think of this as either vertex form or intercept form. I'm going to choose to think of this as standard form. Let's factor. So here for my x-intercepts, I'm going to find them by plugging in 0 for y, and then I'll use them to find my vertex. So here I get 0 is equal to negative 3x squared plus 12. So here, let's do some inverse operations. I'm going to subtract 12 from both sides. Negative 12 should be equal to negative 3x squared. Divide both sides by negative 3 to get 4 is equal to x squared. And then I'll take the square root of both sides to get rid of my square. Here, plus or minus 2 is going to be equal to x, which of course means if I've got my two options, then either positive 2, 0 or negative 2, 0 could be my solution. Of course, both of these are x-intercepts of my graph. So I've got 2, 0 and negative 2, 0. Now for my vertex, I know that my vertex needs to be halfway in between 2 and negative 2. So let's find our average by adding them up and dividing by 2. Well, 2 plus negative 2 is 0, and 0 divided by 2 is 0. So the x value of my vertex is at 0. Plugging in for y, I know that my y value is going to need to be negative 3 times 0 squared plus 12. Well, negative 3 times 0 squared, that cancels out. So that tells me that 12 is going to be the y value of my vertex. Let me write that up at the top. So x is 0, y is 12. And if I were to think of this in vertex form, I should confirm that, right? I did not go left to right, and then I moved 12 up. So the point 0, 12, let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 should be right up here. Cool. From here, I know my axis of symmetry, x equals the x value of the vertex, which is 0. I won't bother to sketch that in. It's my y-axis. Let's find one more point. Maybe I could use the y-intercept, but in this case, you'll notice, right, 0, 12 is already my y-intercept. So let me find one more value and use my symmetry. Choosing a nice number I have not used close to the value of 0, let's try x equals 1. So if x equals 1, then the y value should be equal to -3 times 1 squared plus 12. Let me actually draw a little line here to delineate. This is not my y-intercept. So here y is going to be equal to -3 times 1 plus 12. -3 times 1 is -3, and -3 plus 12 is 9. So if x equals 1 and y equals 9, that tells me that the point 1, 9, so here's 12, 11, 10, 9, should be on my graph. Last but not least, by symmetry. I moved 1 over to the right to get to this point. Let's move 1 over to the left. There should be a companion point right over here at -1, 9. Connecting everything with a parabola to the best of my ability. Again, it don't need to be perfect. And it won't be, because nobody's going to see this video. Just watch this be the video that blows up. Here's my parabola. There we go. Let's find some characteristics. So, now you'll notice my vertex is at the top. It is the maximum value, which makes my parabola concave down. It's a frowny face. However, my domain is still always all real numbers. My range here, so my y values cap out at 12. That means I could go all the way up to 12 or anywhere below. So off to -infinity. Max is out at 12, right? It's a point on my graph, so it gets a closed bracket. Here I increase to the left of the axis of symmetry, which is at x equals 0. If I want to be to the left of x equals 0, then I would be all the way off to -infinity, capping out at that 0. I decrease to the right of 0, which means I go from that value of 0 all the way off to +infinity. Last but not least, let's try this friend. Y equals -2, quantity x minus 2 squared minus 1. Notice this is in vertex form. I can immediately find my vertex. That -2 inside of the square tells me that I went 2 to the right, opposite of what I expect. That -1 outside of the parentheses tells me that I went 1 down. So my vertex is at the point 2, -1, which is right over here. Let me label it 2, -1. And my axis of symmetry, x equals my value from my vertex. So x equals 2. I'll sketch that guy in. Here is my beautiful, perfect vertical line. From here, I need to find some other stuff. Let me start with the x-intercepts. So to find the x-intercepts, right, I'm going to plug in 0 for y and solve for x. So 0 is going to be equal to -2 times the quantity x minus 2 squared minus 1. Adding 1 to both sides, 1 is going to be equal to -2 times the quantity x minus 2 squared. And then I'll divide both sides by that -2 to get -1/2 is equal to my square. Now to get rid of the square, I should take the square root of both sides. But you'll notice here, alarm bells, alarm bells, alarm bells. I'm taking the square root of a negative number. This does not exist. In context, of course, what that means, if I do not have any x-intercepts, I don't cross the x-axis anywhere. This graph is going to be entirely below our x-axis, which means I'm going to need to find some other points. But I should still be able to identify my y-intercept. Let's do it by plugging in 0 for x. When I do so, y is going to be equal to -2 times the quantity 0 minus 2 squared minus 1. So I've got -2 times -2 squared minus 1. -2 squared is 4. So I've got -2 times 4, which is -8. And -8 minus 1 is -9. So my y-intercept here, x is 0, y is -9. The point 0, -9 should be on my graph. So 1, 2, 3, 4, 5, 6, 7, 8, 9 down here on my y-axis. Beautiful. On the other side of my axis of symmetry, right, I went 2 to the left. Let's go 2 to the right. So that tells me that there should be a point right over here at positive 4, comma negative 9. Now again, I just need one more point on my graph. So I'm going to choose a nice value that I have not used close to my value of 2 for my vertex. Let's once again use x equals positive 1. Substituting in here, y is going to be equal to negative 2 times 1 minus 2 squared minus 1. So this is negative 2 times negative 1 squared in parentheses minus 1. Negative 2 times negative 1 squared, well, that's negative 2 times 1 minus 1. Negative 2 times 1 is negative 2. Negative 2 minus 1 is negative 3. So if x equals 1 and y equals negative 3, that tells me that the point 1, comma 1, 2, negative 3 is on my graph. By symmetry, I went 1 to the left. There should be a companion point right over here, 1 to the right, at 3, comma negative 3. Last move, draw the parabola to the best of our ability. And we're happy. Last but not least, let's identify our characteristics and get out of here. So my graph is concave down, which makes my vertex the maximum. My domain is always all real numbers. My range here caps out at this y value of negative 1, which means it can go all the way down to negative infinity, but the maximum it can get to is negative 1 with the square bracket because it's a point on my graph. I increase to the left of that x equals 2, so I can go all the way off to negative infinity, but I cap out at that 2. And then I decrease over to the right of x equals 2, so I go all the way off from 2 to positive infinity.